Download this code from codegive.com, link in the description below. OK, let's dive into a detailed exploration of the Trusted Computing Base, TCB, as it relates to CISSP Domain 3, Security Architecture and Engineering. We'll cover the core concepts, components, principles, and provide a mind map outline, then touch on code examples to illustrate the importance of secure coding practices. Understanding Trusted Computing Base, TCB. The Trusted Computing Base, TCB, is a critical concept in computer security. It represents the foundation upon which the security of a system is built. If the TCB is compromised, the entire system's security is at risk. It's a subset of the entire system, not the whole thing. Definition *: the TCB is the entirety of the protection mechanisms within a computer system, hardware, software, and firmware, that are responsible for enforcing the security policy. This policy dictates what operations are allowed and what are not, and it ensures that sensitive data and resources are protected. It's the trust anchor for the system. Key characteristics of the TCB * enforces the security policy *. This is the TCB's primary function. It ensures that the system operates within the boundaries defined by the security policy. * Small and focused. * Ideally, the TCB should be as small and manageable as possible. A smaller TCB is easier to analyze, test, and verify for correctness, reducing the risk of vulnerabilities. Complexity is the enemy of security. Tamper-proof. The TCB must be protected from unauthorized modification. If an attacker can alter the TCB, they can bypass security controls. This includes physical protection, access controls, and integrity mechanisms. Always invoked. The TCB must be invoked for every security-relevant operation. This ensures that the security policy is consistently enforced. If even a single operation bypasses the TCB, a vulnerability is introduced. Verifiable. The TCB should be verifiable, meaning that its correctness and security can be assessed through rigorous testing, formal methods, or other analysis techniques. Isolation. The TCB should be isolated from the rest of the system to prevent non-TCB components from interfering with its operation. This protects its integrity. Components of the TCB*. While the specific components can vary depending on the system, some common elements include operating system kernel. The kernel is the heart of the OS and often a core part of the TCB. It manages system resources, handles security functions like access control, and mediates interactions between applications and hardware. Security Reference Monitor, SRM, a key abstract component of the TCB. The SRM is responsible for validating access requests. It must be complete mediation, every access is checked. Isolation, protected from unauthorized alteration. Verifiability, its correctness can be verified. Hardware Security Modules, HSMs, dedicated hardware components that provide secure storage and processing of cryptographic keys and other sensitive data. Trusted Platform Module, TPM, a hardware chip that provides security functions like secure boot, key storage, and attestation. Hypervisor, in virtualized environments, the hypervisor that manages virtual machines becomes a critical part of the TCB, responsible for isolating VMS and controlling access to hardware resources. Firmware. Low-level code that controls hardware components, such as the BIOS or UEFI. Secure boot processes rely on trusted firmware. Security applications. Specific applications dedicated to security functions, like firewalls, intrusion detection systems, and anti-malware tools, but only those involved in enforcing the core security policy. Cryptographic libraries. Libraries that provide secure cryptographic functions, such as encryption, hashing, and digital signatures. These must be carefully vetted and used correctly. Trusted paths. Secure communication channels used to establish a trusted connection between the user and the TCB. For example, pressing Ctrl plus Alt plus Del on a Windows system is intended to create a trusted path to the logon process. TCB principles. Least privilege. Grant users and processes only the minimum necessary privileges to perform their tasks. This limits the potential damage if an account is compromised. Separation of privilege. Require multiple conditions to be met before granting access to a resource. This makes it more difficult for an attacker to gain unauthorized access. For example, requiring both a password and a biometric scan. Defense in-depth. Implement multiple layers of security controls to protect against various attack vectors. If one layer fails, others are in place to prevent a breach. Minimization. Reduce the attack surface by disabling unnecessary features and services. A smaller attack surface makes it harder for attackers to find vulnerabilities. Economy of mechanism. Keep security mechanisms as simple and straightforward as possible. Simpler mechanisms are easier to understand, verify, and maintain. Fail-safe defaults. Default to a secure state in case of failure. If a security mechanism fails, the system should automatically revert to a secure state. Complete mediation. Every access to every object must be checked for authorization. No exceptions. Open design. The design of the security mechanisms should be publicly available, though the code itself may not be. This allows for scrutiny and independent verification. Kirchhoff's principle. Relationship to CISSP. Domain 3, Security Architecture and Engineering. Domain 3 focuses on the principles and practices of designing and implementing secure systems. The TCB is a central concept in this domain because it provides a framework for building secure systems. Understanding the TCB helps security professionals. Design secure architectures. By identifying the critical components that must be protected and ensuring that they are part of the TCB. Implement secure controls. By selecting and implementing security controls that effectively enforce the security policy within the TCB. Evaluate system security. By assessing the size, complexity, and trustworthiness of the TCB. Identify and mitigate vulnerabilities. By analyzing the TCB for potential weaknesses and implementing mitigations to address them. Understand the impact of changes. When making changes to a system, understanding the TCB helps to assess the potential impact on security. Mindmap outline, 3 of 9 CISSP domains, security architecture and engineering, TCB focused. Code examples, illustrating secure coding practices within the TCB's scope. Let's look at some code examples to illustrate how secure coding practices contribute to a strong TCB. These are simplified examples, but they highlight important principles. Consider that cryptographic libraries and system calls used in these examples are often part of the TCB itself. 1. Input validation, preventing buffer overflows. This C example shows how a buffer overflow can occur and how input validation can prevent it. Buffer overflows are classic vulnerabilities that can compromise the TCB. Explanation. The vulnerable strcpy function copies the entire input string into the buffer without checking its length. If input is longer than buffer, it will overflow, potentially overwriting adjacent memory. Asterisk the safe code uses strncpy to limit the number of bytes copied. It also explicitly null terminates the buffer to prevent further issues. The strlen function ensures that strncpy doesn't read beyond the bounds of input if it's not null terminated. Asterisk input validation is critical. Never trust user-provided data. Always check its length, format, and content before using it. 2. Output encoding, preventing cross-site scripting, XSS. This PHP example demonstrates how output encoding can prevent XSS vulnerabilities. XSS allows attackers to inject malicious JavaScript into web pages, potentially stealing user credentials or performing other malicious actions. Explanation asterisk. Asterisk the vulnerable code directly outputs user input without any encoding. If the user enters something like script alert, XSS/script, the JavaScript will be executed in the user's browser. Asterisk the safe code uses HTML special cars to encode special characters, like, and, into their HTML entities. This prevents the browser from interpreting the input as HTML or JavaScript. And underscore quotes encodes both single and double quotes, and UTF-8 specifies the character encoding. Asterisk always encode user-provided data before displaying it on a web page. 3. Error handling, preventing information leaks. This Python example shows how to handle exceptions to prevent sensitive information from being leaked to users. Explanation asterisk. Asterisk the vulnerable code re-raises the original file not found error or prints the full exception. This can expose sensitive information, such as the full path to the file or internal error details. Asterisk the safe code catches the exception, logs the full error details to a secure log file, for debugging and analysis, and then raises a generic exception with a user-friendly message. This prevents sensitive information from being leaked to users or attackers. The generic message should never give specifics to the attacker, but should inform the user to contact support. Asterisk proper error handling is crucial for preventing information leaks and maintaining the integrity of the TCB. Log details, but never expose sensitive information to the user. 4. Authentication and authorization asterisk. This is more conceptual but critical. Consider a simple login function. Improvements towards TCB principles. 1. Password hashing asterisk store passwords as securely hashed values, never in plain text. Use a strong hashing algorithm like Argon2, BCRYPT, or SCRYPT. 2. Salting asterisk use a unique salt for each password. This prevents rainbow table attacks. 3. Least privilege asterisk after login, only grant the user the minimum privileges necessary to perform their tasks. 4. Proper authorization checks asterisk before allowing a user to access a resource, always check if they have the appropriate permissions. This check should be part of the TCB. 5. Cryptography asterisk. Important considerations regarding cryptography in the TCB asterisk. Key management asterisk securely generate, store, and manage cryptographic keys. Key compromise is often the easiest way to break encryption. HSMs are often used for key management in sensitive systems. Algorithm selection use strong, well-vetted cryptographic algorithms. Avoid weak or outdated algorithms. Follow industry best practices. Random number generation use a cryptographically secure pseudo-random number generator, CISSP, for generating keys and other security-sensitive data. Insecure random number generators can be predictable and exploitable. Side channel attacks be aware of side channel attacks, which can leak information about cryptographic operations by measuring timing, power consumption, or other physical characteristics. Implement countermeasures if necessary. In summary, the TCB is a fundamental concept in security architecture. By understanding its principles, components, and how to implement secure coding practices, you can build more secure systems and protect against a wide range of threats. Remember that a compromised TCB can have catastrophic consequences, so it's essential to prioritize its security. Focus on minimization, isolation, and continuous verification. The CISSP exam will test your understanding of these concepts and your ability to apply them in practical scenarios. Good luck.